Start recording. You can do it. There we go. Okay, good. So last time, I guess we started integration in earnest, actually defining things and starting to prove some basic theorems. So today, I would like to recap some of those definitions that we did, since they'll be very fundamental. They're kind of the analog of the epsilon delta definition for continuity, which will be kind of the crux of what we do in this chapter. So, man, my computer's being very slow today.
Question.
Yeah.
Is the absolute value function not integrable?
It is absolutely integrable, which we could guess. I mean, we haven't proven it yet, but you could guess that this would be integrable because integrability, roughly speaking, is saying that there exists a sensible way to assign an area under the curve. So if you wanted to assign an area under the blue absolute value curve between two different regions, then you might say, what is this area? Well, you just break it into two triangles, and we know what the areas of triangles are. So you would add up these two things. So absolute value is definitely integrable. Do not make the converse error again, right? So continuous implies integrable. This is absolutely true. The absolute value function is not continuous.
Oh, right. Integrable is under continuity on niceness.
Yes, yes, yes. So it is not true that if you are discontinuous, you are not integrable. So well, this is just how logic works. Just because A implies B does not mean not A implies not B. It's false that this thing holds. Right. Good. Good question, though. Good. Okay, so we'll then see some more integrable functions. The only functions that we know how to integrate from last time are constant functions, which is not especially interesting. Then we will mostly prove this thing, which, as you say, integrability is below continuity on the niceness scale, so indeed every continuous function is automatically integrable. So we'll mostly prove this modulo some small subtlety that we haven't discussed yet, and that subtlety is something called uniform continuity, which we really should have discussed in chapter 2, but I kind of put it off because there was a lot of work to do there, and I didn't want to pile on more stuff. But now we have to kind of pay the piper and go back and really understand what this means, because we need that for this proof. So good. Questions or thoughts on the roadmap?
No questions. No avocados.
No avocados either. Damn it. Avocados are fucking delicious. Okay. So first the recap. So you will recall the problem we're trying to solve is assigning this area, or really assigned area, under a function, which is bounded on an interval. And the idea that we kind of proposed last time was partitioning, cutting up the interval into several pieces, labeled by these t's from maybe t0 up to tn, where here n equals 4, and then approximating the area in two ways with lower and upper sums. So we saw that last time, and I have some definitions to remind us of what those things mean. So a partition is simply a finite set, a collection of points which lie in the interval, one of which is the left endpoint and one of which is the right endpoint. So you can think of this as just chopping up the interval into some number of pieces, I guess n pieces if there's n points in the partition. So that's a partition, and then we used the notion of partition to define lower and upper sums. So on each of those subintervals, the ti minus 1 up to ti's, we take the infimum, the greatest lower bound of the function values on the interval, and the supremum, the least upper bound, and use those to define lower and upper sums. So the lower sum is kind of the dark gray, squares or rectangles, I guess, rectangles. We use the infima times the widths, the lengths of the intervals, and for the upper sum we use the suprema. That was the light gray rectangles. Okay, so these were our two notions of sum, lower and upper sum. Then we defined integrable. So a function is integrable, or in other words, it has a well-defined integral on this closed set from a to b, if the supremum of all of the lower sums, so the least upper bound of all of the lower sums, is the same as the greatest lower bound of all of the upper sums. That is the greatest lower bound of the upper sums, if you will. So we kind of justified this last time by showing that, as partitions become finer, the lower sums get larger and the upper sums get smaller. So you would hope that if there's a sensible point that they both approach, that the supremum of the lower guys would be the infimum of the upper guys. So if that's true, which is true for certainly every continuous function, as we'll see, if these two things are equal, then we call their value the integral, which is this thing, which is just an area. and then we found the area of a constant function, under a constant function last time. The last thing we did last time was this reformulation. Since to prove something is integrable, we have to do this supremum equals infimum business, which is a bit difficult to work with. So we proved an equivalent way of saying that a function is integrable, which is to say that for every epsilon greater than 0, you can find a partition such that the upper sum minus the lower sum in that partition is smaller than epsilon. So we proved this last time, and I want to revisit one step in that proof, which I kind of botched last time, but will make more sense now that you've done today's daily challenge. So that was this step in the proof when we were doing the converse. Right, so I said, suppose the function is integrable, which means it satisfies this definition that the infimum of the upper sums equals the supremum of the lower sums. Or in other words, subtracting. This means that, kind of sloppy notation, the infimum of all the u's minus the supremum of all of the l's, just subtracting the supremum onto the other side, this thing is 0, which is certainly less than epsilon for any positive epsilon you could choose. Now, the thing I botched last time was how do you go from this step to this step? This step said, now we got rid of the infimum and supremum. We are speaking now about specific upper and lower sums in specific partitions, p and p prime. Well, the way to do that is just to use the results that you proved in the daily challenge today, which is simply that if, alpha, say, is the supremum of some set, say all of the l's, then for any epsilon greater than 0, although here we really want to use, I guess, epsilon over 2 maybe, for maybe epsilon over 2, there exists an element in the set of all the lower sums. You prove that for any epsilon, there has to be some element in this set with alpha minus, or sorry, what letter should I use for the lower sum? I guess just the lower sum. I should use L. There must be some lower sum in the set of all lower sums. Now my notation's getting very sloppy. Alpha is the supremum of all the lower sums, so that means that whatever epsilon I pick, there has to be some lower sum with the property that the lower sum, let's see, what is it, plus, or is it minus? Yeah, there has to be one where, what am I trying to say? There's supposed to be one that is between alpha minus epsilon and alpha, right? So trying to say that there is an L is L in the set with L greater than alpha minus epsilon over 2. There we go. Took me too long to do that. This is what you proved, that if alpha is the supremum, no matter what epsilon you pick, you have to have some guy between alpha minus epsilon and alpha. Because if there were no such guy in that range, then you could just take alpha minus epsilon over 2, and that would be a new least upper bound, right? This was the proof by contradiction. So you simply use this argument to say, okay, well, there has to be some partition. Now I'm switching from the L's to the P's, I guess. There has to be some partition, which gives me in, say, the lower sums, there has to be one in here, which would be some partition P prime, or I guess for the lower sums I've been using P double prime, with, say, L of P double prime greater than the supremum minus epsilon over 2. And you do the same thing here for the infima. Here I think the proof we used beta and y or something, but there must be some P prime with the upper sum in P prime must be less than, I think, the infimum plus the epsilon over 2, or something like this. Okay, so the point is that if the infimum minus the supremum is upper bounded by some epsilon, we can pick specific elements of the sets, maybe a P prime and a P double prime, that are sufficiently close to the infimum and the supremum so that you could get this inequality between not the infimum and supremum, but specific elements of those two sets. I think I picked the fractions incorrectly now, because, let's see, this would be less than in. No, this is correct, I think, because maybe I should rescale. For this epsilon, I should have picked this guy to be 2 epsilon or something. Yeah. So this is the exploration when you go through and then find what numerical factors you needed to go back and make it work. So I should have at the beginning of the argument said this thing was 0, certainly 0 less than twice epsilon, where the epsilon was the one handed to us, and then you would go back and use this argument for from the proof that you did today in the daily challenge and pick epsilon over 2 twice. And then you get an epsilon over 2 minus a minus epsilon over 2, which would give you an epsilon, and you would subtract the epsilon from both sides to kill off one of these 2 epsilons, and then you would get u of f in p prime minus l of f in p double prime would be less than 2 epsilon minus epsilon is epsilon. So that's the way I should have done it, but I was confused about the factors of 2. Okay. So the point is that this step in the proof we did last time follows from 2 applications of the results from your daily challenge earlier today. Good. Okay. Thoughts on this thing?
I have no thoughts.
Okay. Is that thoughts T-H-O-U-G-H-T-S or T-H-O-T-S?
The former.
Okay, good. Probably also the latter, but that's unrelated. Okay, good. So now that we have rectified that small hiccup from last time, let's construct more functions which we will know to be integrable. So the first example is what I call kind of changing a point or moving the definition of a function by 1 point. So here's a challenge for you. We define a function f of x, which is 0 most of the time. So it's 0 at almost every point on the real line, despite, well, ignore this, that should be like 0. And then we define it to be 1. So this function jumps up from 0 to 1 at a single point. It's 1 at x equals 1, and it's 0 elsewhere. So this thing is certainly not continuous, but I will ask you, if we pick a specific interval, maybe say the closed interval from 0 to 2, do you think this function is integrable on 0, 2? And if so, what should its integral be?
I do not believe. Oh, I believe it is integrable, but its integral is 0.
Okay, so you say yes, integrable, and integral of f from 0 to 2 equals 0. Okay, so no proof required, but what went through your head, or what were the mental steps in arguing for this?
So the only thought I really had is the idea of area going from 0.9 repeating up to 1 and back down to 1.0 effectively repeating. That's going to be a line, and therefore doesn't have any width, and it doesn't have any area.
Yeah, that's a good way to think about it. So you're saying, my pen just broke. Come on. Well, I'll talk while this. There we go. So you're saying, and it broke again. Well, I mean, roughly you're saying, let's think about this as a really, really skinny. There we go. You're saying this is roughly a really skinny triangle, right? It goes from 0, then jumps up to 1 for like an infinitesimal. That word doesn't mean anything, but roughly speaking, an infinitesimal width. You say it jumps up to 1 and jumps back down. But you're saying really this width is going to 0. So the contribution to the area from this infinitesimal jump up to 1 and jumping back down should really be the height, which is 1, but the width is also 0, so the area of this blip, this little blip on the radar, should really be 0. So you're saying the area of the blip at this point is 0, and clearly the area on the rest of this interval is 0 because it's just constant. So you would say the integral over this interval should also be 0. Is that roughly what the idea was?
Yeah.
Okay, good. Yeah, so that is correct. In fact, you can generalize this. I don't know if I'll ask you to write this out, but you can generalize this argument to show that for any function, if you move a single point it will not change the value of the integral. So if you have some function and you can find it the area under its curve, if you move it at one point, the integral doesn't change and it remains integrable. And in fact, you can even generalize this to changing a finite number of points. If you move, finitely many points, maybe I pick 100 points on here and move it all up to like random numbers like 1 or a million or something, the area will still be 0. So changing finitely many points will never affect the integral, but I'd like to actually prove that for you, at least for the 1 point case. So what is the proof that this guy is indeed integrable? Why did I write an F there? That should be 2. This guy is integrable and his integral is still 0. Well, here's the proof. So we're going to pick a partition, so let P be this partition which starts at t0 and goes up to tn, and we're going to say, man, I screwed this one up. It should be tj. So basically we have a bunch of these partition points, t0, t1, up to tn, and the point of interest, that single interesting point where this function jumps up to 1, that guy has to occur between some pair of these t's, right? It happens somewhere. So we just say, all right, well, let's name the t where that happens. The left one will be tj minus 1, and the right one will be tj. Right, so we're just picking j as the index where, you get the subinterval where this guy jumps up to 1. Okay, fine. So we do that. Then we ask, well, what are the infimum and supremum on all the subintervals? Well, on all of the guys except the j, this function is constant, right? He stays at 0, so on every subinterval except the j guy, both the supremum and infimum will be 0. The only interesting one is the j guy. On the j guy, clearly the infimum is still 0, but the supremum is 1, because this guy jumps up to 1. Okay, so, man, how are there so many typos today? -1. So the lower sum, I'm just splitting it up into 3 pieces. So this is the sum of all of the guys before j, so these guys on the left. It's all of the infima times the length of the subintervals, but these are all 0. Then there's the j guy, so this is the j guy times the length of the j interval, which is, well, still no contribution because the infimum is still 0 there. And then the sum from j plus 1 up to n, so this is all the guys to the right of the j guy, still 0. Okay, fine, so the lower sum is always 0 in any partition. What about the upper sum? Well, for the first j minus 1 guys, still the supremum is 0. And for the last guys from j plus 1 up to n, the supremum is also 0. The only interesting one is the middle jth guy, where the supremum is 1. So the only contribution to the upper sum is from the jth guy, which gives me 1 times tj minus 1, which is this. Okay, so that means the difference, remember the thing we have to show is less than epsilon to make this guy integrable, is the difference between the upper sum and the lower sum. But that's very easy because this minus 0 is still tj minus 1. Okay, so now we're almost done. We just have to prove that given any epsilon greater than 0, I can pick a partition with the property that tj minus 1 is less than epsilon. But that's very easy to do, right? You can pick any partition you want. We can even pick a very, very simple partition with just 3 points. You start with t0 equals the left endpoint, which is 0. Then, I guess 4 points really. t1 is going to be, let's see, 1 minus epsilon over 2. t2 will be 1 plus epsilon over 2. And then the last one, t3, will be 2. So here's my very simple partition, right? Just split it up into 4 intervals, and this has the property that the tj guy, the guy that contains 1, this guy has width, well, equal to epsilon. So I guess I should make this a little smaller, because we have to make it less than epsilon, so maybe I should make this epsilon over 4. So his width will be epsilon over 2, which is certainly less than epsilon. So epsilon over 4, whatever. Okay, well, you get the point. I mean, you can always pick partitions so that the guy which encloses 1 is smaller than epsilon. You just tune this to be very small. Okay, so that completes the proof that this function is integrable, but it doesn't tell us what the integral is, the actual value. we want to prove that's 0. But that's also very easy to do because clearly the lower sum is always 0, so L is less than or equal to 0. The upper sum is always tj minus 1, which is strictly positive, actually. This guy can never go negative, so that gives the second half of the inequality. The upper sum is always greater than or equal to 0. So that means that when we take this difference very small, since the distance between the left and the right guys is getting arbitrarily small, less than epsilon, but this almost a squeeze theorem type argument tells us that if L and U are approaching the same value and they're kind of straddling 0 on either side, then the only value that they can both approach is actually 0. So by taking this middle part of the partition arbitrarily small, we've proven that the integral of this function from 0 to 2 is 0, as you thought. Good. Comments on this?
I do not have any thoughts, questions, or comments.
Or death thoughts. Oh no, why is there a slack? Straddling. Yes. I probably shouldn't use that word.
What?
I probably shouldn't use the word straddling.
Why not?
I don't know. Okay, good. Well, let's do something more interesting. So that was just a constant function where we moved a point. So let's reproduce some results from 10th grade geometry. So I will ask you, suppose we define the function f of x equals x. So just this straight line with slope 1. And, ooh, interesting. And now I ask, what is the integral, what is the area under the curve of this line between 0 and some arbitrary point b? So we want to find this area here. So I claim that we actually don't need calculus to do this. We can just write down the area from geometry. So what do you think this area should be?
I believe it should be half of x squared.
Well, this point's b. So this point's b, yeah. Half b squared. Good. Yeah, so this is just a triangle. So this is quite easy to show. I mean, well, probably in your geometry class you never proved the area of a triangle is a half b squared, but
we did not.
Well, right, okay. Well, I'm not going to do it either because I don't want to. I want to do calculus. So,
Yeah.
Okay, well, if you believe this for whatever reason, then yes, indeed. The area under this guy should be a half b squared. But if we want our new definition of area from calculus to agree with what your geometry teacher told you, then we should prove this using lower and upper sums. So this is a bit more interesting. Let's do that. As you say, we should certainly expect that this integral is a half b squared. But to prove it, we first have to show the function is integrable. So if someone hands us an epsilon greater than 0, we have to build a partition, or construct a partition P, with the property that u minus L in that partition is less than epsilon. So I'll show you a way to do it. This is kind of the easiest thing you could do. If we have to build a partition, you might think, okay, the easiest partition you could think of to do is to say, well, we're going to chop up the interval from 0 to b into n equal subintervals, right? So you start at t0 equals 0, and then you have this t1, which is maybe just b over n, because we're chopping it up into n little chunks. So then you have a b over 2n, or sorry, 2b over n, 3b over n, and like maybe the jth guy is going to be j times b over n, blah blah blah, and then the last one is b. So we're just chopping him up into n equal subintervals. Okay, so let's see if this partition does the trick. So what is the lower sum? Well, the lower sum is the sum of the lowercase m sub i's, which is the infimum. Well, the infimum is very easy to see for this line because clearly y equals x is strictly increasing. So the infimum on any interval, maybe ti up to ti plus 1, you can see the lowest, the infimum, is going to occur on the left endpoint. So the left endpoint on the line y equals x, well, the x value is t sub I, the y value must also be t sub I. So that means the infimum on the interval ti to ti plus 1 is t sub I. Okay, but unfortunately I've I've here used the notation ti up to ti plus 1, but in the definition of lower sum, I now realize it's ti minus 1 up to ti. So what I really should have said over here is, you can think of this as re-indexing because I derped in real time. It would be ti minus 1 on the left and ti on the right. It's the same thing, just changing the definition of I. Okay, fine. So you say, fine, the infimum is the left endpoint. So by definition, I take the infimum times the length of the interval, and I add up all of those from 1 to n. Okay, so that's pretty easy to do because we know what each of the ti's is, right? Each t sub I from this definition here is I times b over n. So ti minus 1 is I minus 1 b over n, right? That's pretty easy. And the length of an interval, what's the length of an interval? Well, that's one of these guys minus the one before him. But we've chosen these to all have the same length, right? 2b over n minus b over n is b over n. I plus 1b over n minus ib over n is b over n, whatever. So all of these widths, I should call them, all of the widths are going to be the same, b over n. Okay, fine. So then I just do some algebra. I take the b and the n upstairs and move them out. So I have a b squared n squared here. I'm left with an I minus 1 inside the sum. So there's a sum from I equals 1 to n of I minus 1. Question for you, what did I do in this step?
I just got distracted by whatever that awful clicking.
Was that on your end? I heard something rolling. It sounded like a coin rolling and then flattening.
No, that was pipes.
Pipes?
It's crazy. Constantly.
What if one of them springs a leak and your basement starts flooding?
That would suck. Actually, how quickly could I get everything out of here? Not very quickly. Regardless, let's see what you did in this step. It seems that you kind of re-indexed it.
Yeah, exactly.
Moved everything. I say, like, kind of moved everything to the left by 1.
Yeah, so I just, this is, you're probably having flashbacks to that Leibniz formula with the re-indexing fuckery.
Yes.
So yes, there's some re-indexing fuckery where all I did was define j equals I minus 1. Right, so if j is I minus 1, this I minus 1 becomes a j. I equals 1, well, you subtract 1, so that goes to 0, and you subtract 1 goes to n minus 1. So all I've done is re-index to make the sum and I minus 1 look nicer. And we'll see why in a moment, because we want to compare this to the upper sum. Okay, good, so that was some Yeah, it's not magic, it's just fuckery. Okay, good, so that's the lower sum. What's the upper sum? Well, first, I guess we should evaluate this first. Okay. Another reason to reindex is now it's very clear how to add this up, right? Because we have this nice formula that we saw a while back in this Harvard-MIT math tournament problem. What if you want to sum the first, I guess, n integers, right? I equals 1, or k equals 1 to n, k, this is 1 plus 2 plus dot 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 up to n. What if you want to add up the first n integers? Well, we saw this when we were adding up the first 100 integers, and you maybe even proved this by induction, but the trick is very simple. You just pair these guys off, right? You pair up 1 with n, and 2 with n minus 1, and so forth. So we're going to get a bunch of copies, basically. We're going to get n, well, each of these pairs is going to be n plus 1, right? 1 plus n, 2 plus n minus 1, they're both n plus 1. How many of them are we going to get? Well, there's going to be, let's see, if there's an even number of these, we have to be careful if there's an odd number, but if there's an even number of them, we're going to get n of them. And if there's an odd number, you can show as well by induction that the same formula works, I think. You just pair them, and then the middle guy is going to be exactly halfway in between, so he contributes the missing one that you would have gotten in the odd case. So anyway, I mean, we've seen this before, so I won't belabor the point, but the punchline is that this lower sum asks us to add up the integers from 0 to n minus 1, and we've seen before a formula for doing that. To add up the first k integers, you just take k times k plus 1 over 2. Okay, so fine, I just used that in the previous formula. I've taken this sum on j and replaced him by n minus 1 times, I guess, skipped one step here. This is supposed to be, let's see, to 0 to n minus 1. This would be n minus 1 times n minus 2 over 2, I guess. Is that right? Sum up to n times b squared over n squared. I think I'm doing that correctly. Then you would have an n squared minus 3n plus 2, I think. Then I believe if we simplify, if I can do some algebra on the fly, yeah, I think we should, I may have screwed up the previous one, but, k plus 1. I did it wrong, yes. So indeed, it should be n minus 1 times n over 2 times the b squared over n squared. That's what we should have. And then one factor of n cancels, and we get this thing. Okay, good. So anyway, algebra aside, that gives us the value of the lower sum. It's this guy. The upper sum is very similar, except in this case, the supremum of this function on any interval is the right endpoint, so that is t sub I in this notation. So now we're adding up from 1 to n, the supremum t sub I. Well, we chose these guys to be evenly spaced, so each t sub I is ib over n. The width of every interval, again, the width is just b over n. So we're getting, now this is, I guess, the sum from I equals 1 to ni times b squared over n squared. We know how to evaluate this sum. We just use this formula. That should be n times n plus 1 over 2 times b squared over n squared. Cancel a factor of n. And now, as you see, we get n plus 1 over n, one factor of n left, times b squared over 2. Okay, so a lot of sum and re-indexing fuckery, but at the end we get this expression for the upper sum, this expression for the lower sum, and you can kind of see by eye, if you take the difference between them, the bottom one minus the top one, well, you can factor out a b squared n over 2, and then you have an n plus 1 minus n minus 1, which is 2, I think, and the 2's cancel, and therefore the difference between the upper sum and lower sum is b squared over n. Okay, good. But now if we think back and remember, what are we trying to prove? We're trying to prove that that difference can be made smaller than any epsilon. So if you hand me epsilon, then I would say, all right, I'm just going to pick the number n of evenly spaced pieces in my partition. I would say pick n equals, I guess, b squared, or I guess to make it greater, I should say pick n greater than b squared over epsilon, right? Because then clearly u minus L is going to be less than b squared over what is n, and is greater than b squared over epsilon, equals epsilon. So that's pretty easy. Just pick n big enough. So that proves that the line is integrable. The linear function y equals x is integrable, but we don't know what the integral is. Well, again, that's pretty easy to prove. So again, we want to do this sort of squeezing type argument. So let me erase all this junk. But I claim that just by looking at these formulas, we can get a lower and upper bound. Why is that? Well, in the lower sum, we have this number times b squared over n. But this number is n minus 1 over n. And n minus 1, well, n minus 1 is always smaller than n, so their ratio is always less than 1. In the upper sum, n plus 1 is always greater than n, so their ratio is always greater than 1. So that means the upper sum is always bigger than b squared over 2. The lower sum is always less than b squared over 2, I guess less than or equal to. So if these guys are going to approach the same value, the only value they could approach is b squared over 2. So at long last, we have proven that the integral from 0 to b of f, where f is here x, is b squared over 2, which we would have expected from the triangle argument. Good. So we have we have reproduced 10th grade geometry, which you probably spent a mind-numbing amount of time going through with Berna yesterday. But okay, thoughts on this, or is this all clear?
I have no thoughts on this specifically. I'm trying to think about how I can explain taking the face of a prism and multiplying it by its height.
Face of a prism. Why do you want to use the face of a prism?
Because you can get the volume of any prism by seeing its face and then multiplying by its length. Or
Oh, I see. Okay, so you're trying to generalize this to volumes already. My pen just.
oh, I'm just thinking of Berna stuff.
Oh, it was the work you were doing yesterday on volumes of prisms already? This early in the year?
Yes.
I thought usually solid geometry happens like at the end of the course, or am I confused?
Prism. What's two faces? Those.
Oh, you mean like a parallelogram, not like a solid prism.
I mean a 3D object, of course.
Oh, okay. So you want something that looks like, I don't know,
Right.
like a parallelepiped is the word we use in math. So you want some guy that has some three-dimensional shape like this. I don't know. Oh, that's not what I want. Something like this.
Got it.
And you want some volume. Yeah, you can actually find the volume of this guy by integration as well. We just have to do a 3D integral. So you do
Oh God.
triple integral of some slicing. You slice this guy up, and then people often write this as dv, which is, or maybe a better way to do it is the area of a slice times dx. So you kind of slice this guy into a bunch of faces. Each face has area A. You multiply by a small width. But yeah, this is the sort of thing you do in a multivariable calculus course, is slicing up 3D objects and using that to find their volumes. Good.
Wow.
Good. That's a very productive question. Other thoughts or questions?
I don't even think it was a question.
Well, I guess comment, yeah. You said you were thinking about something, but good. Other things.
MIT Splash.
Oh, yes, that starts, what, in 15 minutes? The first come, first serve?
Yep.
Okay, we can take a break in 15 minutes if you want to sign up for classes.
I'll see what I can get.
Okay, good. Well, I will keep that in mind. Alright, let's see if we can finish Act 1 before that thing opens. So, let's do the first non-trivial integral calculation of our calc group. So this is by non-trivial, I mean we're going to get a result that you would have never guessed using just geometry. We're going to try to find the area under a parabola. So let's start with the simplest parabola, just y equals x squared, right? The simplest thing you could think of. There is no way, to the best of my knowledge, that you can ever find the area under a parabola between, say, 0 and b for simplicity without using calculus. So let's do that. It looks like a complicated region. It has this curved boundary. We don't know how to handle curved boundaries in a geometry class, so we just have to do it. Just have to compute. So we'll try to repeat the same sort of reasoning we used for the line and partition the interval from 0 up to b into n equal parts. So same thing. We start with 0, and then this goes up to b, so we want one which is just b over n, 2b over n, dot dot dot, maybe n minus 1, b over n, and the last one is b. So same as before, just chop up the interval into n equal parts, and now we have to do the lower and upper sums. So now it's a bit trickier, but we still know, let me redraw what, damn it. My drawing skills are tending to 0 more rapidly than I'd hoped. So here's the parabola x squared. So on each subinterval, since this guy is still strictly increasing, which you can actually prove now since you know his derivative on this half line, x greater than 0, his derivative is always positive, so this guy is strictly increasing, so you can prove that now. Because he's strictly increasing, when we take the lower sum, which means we're plugging in the value of the function at the lowest point, or the infimum, if you will. The infimum will always be the square of the left endpoint, because that's the smallest value it achieves. So this lowercase m sub I is going to be ti minus 1 quantity squared. Okay, so that's the infimum. As always, you multiply by the width. So what are we doing here? We're just finding the area of this lower triangle, so it's ti minus 1 squared times the width, which is ti minus 1. Now we're just using a little bit of algebra trickery, so since we're chopping this guy up into equal intervals by construction, ti minus 1 is going to be I minus 1 b over n. So when we plug that in here, we square this whole thing to get the ti minus 1 squared. I get a b squared over n squared, which I put here, and then I get an I minus 1 squared. Okay, and then I won't ask you this again because it's the same question, but I do the reindexing fuckery again and reindex I minus 1 to j. So now we're summing up all the j squareds, because this guy is j, from 0 to n minus 1, and then I've just pulled out this overall factor b cubed over n cubed. Okay, great, so that's the lower sum. We also need the upper sum, but this is effectively the same argument, so we do the same thing, ti squared. The area of this big blue rectangle over here is going to be the ti squared height times the width, which is again ti minus 1. So that's what I've written here, the area of the blue rectangle. And again, just do the same thing. So ti squared, well, ti is ib over n, so this guy becomes an ib over n all squared, which gives us an I squared b squared over n squared. This guy's a b over n. Combine the b squared n squared bn over to a b cubed over n cubed, and we're left with the sum of j squareds. So these things. Okay, so now you see why I did the reindexing, because you may have asked, okay, Christian, why did you reindex in the second calculation? Why did you didn't change anything. You defined a new variable j, which was equal to the old variable I. Nothing changed. I squared changed to j squared. The limits of summation changed the same from, they stayed the same from I equals 1 to n to j equals 1 to n. Why did you change the name from I to j? And the answer is just to compare these two. Because in the first sum it was a j, so I just wanted to change his name in the second sum to j so I could compare them more easily. And when we do that comparison on the next slide, since we want to take the difference of these two, the difference between the two, well, first I guess I should evaluate the sums. Right, so there is another formula. So we proved a long time ago, and I reminded you a moment ago, that if we sum the first n integers, you get k times k plus 1 over 2. There's another formula, which I won't prove here, but maybe I'll ask you to prove it by induction on a daily challenge. You could ask, what happens if you add up the squares of the first n integers, like 1 squared plus 2 squared plus 3 squared plus dot dot dot. The answer, I mean, it's not hard to show. You get this k over 6, and a k plus 1, and a 2k plus 1. So you could prove that. Maybe I'll ask you to do it, but whatever. So one can prove this summation formula for the squares of integers, and that's very useful because our lower sum and our upper sum both involve the sums of squares of integers. So let's just use that formula directly in those sums. So if I just take this guy, b cubed over n cubed times the sum of the squares up to n minus 1, well, okay, so that's b cubed over n cubed times whatever this formula says when k equals n plus 1. So I'll just plug in n plus 1 everywhere, right? So plugging in n plus 1 gives me that. N plus 1 goes to n. 2 times n plus 1 quantity plus 1 gives me 2n minus 1. And then I do the same thing here where k's are n's, right? So when k equals n, I get a k over 6. Here's the 1/6. Here's the k. Here's the k plus 1. Here's the 2k plus 1. Yeah, it's just algebra, right? So I'm plugging into the formula for k equals n minus 1 and for k equals n in these two lines. Okay, so here is where I will skip one more step and maybe ask you to fill in the details on a challenge, but Now we just have to show that the difference between these two can be made arbitrarily small. So I won't go through it in detail because I might ask you to do it, but you can kind of see by eye how this is going to work, right? So if I take the upper sum minus the lower sum, let's just look. The prefactors are all the same. So if I subtract these, then I can factor this junk in front out. What's going to be left when I factor this junk out? Well, the highest order in the polynomials for each of these will be the same, right? What's the highest order up top? N times 2n is 2n cubed. In the bottom, it's n times 2n, which is 2n cubed. So when I subtract these, the cube piece cancels, and the first non-trivial order in the polynomial I get is a square. So you can kind of see just by subtracting these that u minus L is going to be proportional to, I'm not going to keep track of the numbers because I'll ask you to do it probably, but it's going to be proportional to maybe the b cubed stays, and there will be maybe some, I don't know, there'll be some n squared and, I don't know, an n and maybe a constant, I don't care, but there's still an n cubed downstairs. So the point is that you can see by doing this that when I subtract them, I get something with a square upstairs and a cube downstairs. And as we proved last chapter, in chapter 4, if you have a ratio of two polynomials and the order of the downstairs kills the order of the upstairs, then this guy's going to go to 0 as the variable gets large. So that's the point. I mean, if you subtract these, you're going to get something which is going to go to 0 as I take n huge. So, in fact, I can make this smaller than any epsilon because he's going to go to 0 as n gets large. So, I mean, you can write that out, but that proves that this guy is integrable because the upper sum minus the lower sum tends to 0. And then the last thing is to say, okay, fine, this guy's integrable, but how do I find what the value of the integral actually is? And then we just run the same sort of squeezing argument, right? You look at the lower sum and say, okay, well, this guy, I'm just looking at the cubic term, I guess, is going to have a 2n cubed. I don't know how to write this. Maybe the cubic term. There's a 2n cubed upstairs, a b cubed upstairs, and a 6n cubed downstairs. My 6 looks like my b, unfortunately, but this looks like roughly a b cubed over 3. And the same thing here, if I just keep the cubic term, because I know the other ones will be smaller when n gets large, this guy is also b cubed over 3 plus some junk. So since the lower guy is b cubed over 3 minus some junk, and the top guy, or sorry, the upper guy is b cubed over 3 plus some junk, we know the upper guy is always going to be bigger than b cubed over 3, and the lower guy is always going to be smaller than b cubed over 3. But we've just proven that they approach the same value. So if these guys straddle, I shouldn't have said that, if these guys bound b cubed over 3, and they approach the same value, then they must approach that same value, b cubed over 3. Okay, good. So here's our first non-stupid results of integral calculus. If you find the area under a parabola, just say x squared, between x equals 0 and x equals b, the value of that area is b cubed over 3. And at this point, you are probably itching to
That is very familiar.
Yeah. Let's just highlight this again. So we integrated a constant, which you could say this is like x to the 0 or something. This was CB. We integrated x and found b squared over 2. We integrated x squared and found b cubed over 3. So seeing this pattern, you were probably very anxious to conjecture or guess. You say,
Why is it over 3 instead of over n?
Oh, for fuck's sake, man. This is what happens when I try
Oh, wait, n minus 1. Never mind.
Yeah, over n plus 1, right?
Yeah.
Because it's n plus 1 upstairs. Like plug in n equals 2, right? It should be cubed over 2 plus 1 is 3.
Okay.
Yeah. Good, okay. Yeah, a lot of typos today. But yes, okay. So the pattern certainly seems to be that if you find the area under some curve x to the n up to some point b, it looks like that area is going to be b to the n plus 1 over n plus 1. And this looks, painfully familiar. This looks like the antiderivative, right? This looks extremely similar to the antiderivative. So, indeed, that's what we're working towards. So at the end of this chapter, at the end of chapter 5, we will prove what is called the fundamental theorem of calculus, which shows that in many cases, the integral, the area under a curve, is intimately related to the antiderivative. They are not the same. I cannot stress this enough. If there's one thing that you learn about calculus from me, it should be that the integral is not the same as the antiderivative, but they are closely related. And I would like to make very explicit when we get to the fundamental theorem what the relationship is, and why I don't like when people think that these are actually identical. But, okay, fine. So Splash opens in 3 minutes, so that's very good because that was the end of Act 1. So the end of Act 1 was noticing that, we can find areas under curves. It seems like a huge pain in the ass, but it seems to be related to the antiderivative. And maybe I should, take a break, and then once you're happy with your class registration, maybe we can resume and do the remainder of the slides.
Opening up. Why? I MIT Splash and got Mitsubishi instead.
Mitsubishi Splash